Alrighty, so today I've got a few pages of notes on MOSFETs from a layout perspective, and then we'll play around with electric for a little bit for the remainder of class. Excuse me. Hopefully by Thursday we'll have everything sorted out with everybody able to use it, and also integrate it to LT Spice so that we can do some simulation and good stuff too. All right. So from a layout perspective, a MOSFET is excuse me, actually fairly straightforward. We would define two active regions, or at least this is how it used to be, and we'll talk about that in a moment. And then somewhere in the middle, we would define the dimensions of our polysilicon gate. And from a, oh goodness. So here's our layout or top-down view, and a cross-sectional view would look something like this. So here is an, excuse me, N plus region. Here's another N plus region. We're going to see in the area of the transistor a very thin oxide grown, and then we'll also see our field oxide, which is going to be used to separate this transistor from other transistors. That's a separate step. And then lastly, we'd have our polysilicon gate on top. Sorry, I need to find my asthma inhaler real quick. So a couple of things about this particular drawing here, especially the way that things are done now. This distance between these two, between the polysilicon gate and the active region on both sides, is due to what's called lateral diffusion. And we'll talk specifically about what that does in a moment. But the gist of it is that it's shortening the overall length of the channel. And then we also may have some issues that we can't see in our design right now, where we might have oxide encroachment. So let's say, just for the sake of argument, that the areas, the width dimension here is the overall width drawn minus this little bit where the field oxide kind of just pushes into the transistor a little bit and makes the overall width of the transistor slightly smaller than as is drawn. While we're at it, I'm going to define this guy right here as the effective length of the transistor. Yeah. And so it's simply the drawn length of the polysilicon minus the two lateral diffusion areas. All right, so before we jump in and talk specifically about lateral diffusion, let's talk a little bit more about how a modern transistor is actually laid out. And so one of the big problems that we would see by defining two active regions like so is that if we define two active regions and then a polysilicon region over the top of it, and we have mask alignment issues, it's possible, excuse me, goodness, that we may not form a full transistor because the gate may not be exactly where it needs to be. So a modern approach to get this exact same effective layout would be something like this. We define one large active region, and then we put our polysilicon layer like so. We're going to get the exact same profile, but we are guaranteed that our gate is going to line up over, or is going to overlap the source area and the drain area active regions, because the gate itself is acting as a mask when defining those active layers. So we put the poly down first, use that as a mask, and then do the donor implantation into the active region. And so that's a twofold win there, right? So we have our gate for sure lining up with our source and drain regions. And after the annealing process, we should see that we have the lateral diffusion we need to cause the N+ implants to kind of move slightly under the polysilicon layer so that everything's on the up and up there. And this also causes the polysilicon layer to become highly conductive so that it is able to act as an effective gate, right? And so if our gate were an insulator, for instance, it'd be hard to control the channel and inversion and things like that, because it'd be hard to store charge on it to cause the opposite charge to invert the channel. So this self-aligned gate technique is what's been used for some number of years now. And it's increased transistor yield by a large amount. So I think this may be wildly wrong because I'm trying to remember the last time I read about it, but changing the yield from somewhere around 70% to over 95%, I believe, is what the self-aligned gate technique did with regards to transistor yield. Alrighty, so now let's talk a bit about the specifics of lateral diffusion. So when the source and drain regions are implanted, some portion of the implant dose laterally diffuses out underneath the gate poly layer. This phenomenon shortens the effective channel length as L effective is equal to L drawn minus twice L diffusion. So while some lateral diffusion is arguably good, it can be excessive, and so we can minimize these effects by using a lightly doped spacer implant. The poly before heavy source drain implants are deposited. And so let's kind of look at this process real quick here. So we're going to start. Here's our P substrate. We're going to have some field oxide layer. and our gate oxide here. Let's see, what color was I using for end wells? I think it was red. And these guys right here are undoped poly. So this is what our substrate looks like before our implants. All right. So we're going to use those sections of undoped poly as a bit of a mask. So here's what we had. So we're going to dope, lightly dope spacer implants. Okay, so let's just use this color. So we're going to have a small implant right here and right here where the undoped poly acted as a mask. Right now, these guys are going to be N implants. And over here in our N well, we're going to put a pair of P implants. And so what that does is it dopes our polysilicon, making it conductive. So here we're going to have N poly, and over here we'll have P poly. And these are the lateral diffusion, what are called LDD implants. So they're trying to minimize effects of lateral diffusion. And then lastly, we do our source and drain implants. And so that just means we're going to much more heavily dope a specific region. So we have our implants here and here and here and here. And when we heavily dope, what we're going to observe, something like this. So we have just a little bitty area of that spacer implant, which is conductive. And then we have a much larger area of these N+ implants on this side, P plus implants on this side, and the extra doping that we're getting by doing the heavy concentration source and drain implants is going to give us an N plus poly gate on this transistor and a P plus poly gate on this transistor. So we formed exactly what we want. We have heavily doped source and drain regions. Where for the NPN transistor, the implants are heavily doped N plus with these very small, lightly doped. So instead of calling it N plus, we'll just call it N or N minus doped spacer implants. On the PNP transistor, we have effectively the exact same thing, but it's all sitting inside of the N well. That's the local substrate. And the reason why this minimizes the effects of lateral diffusion is because the concentration level, so diffusion, even in the annealing process and all that kind of stuff, is all about things moving from an area of high concentration to an area of low concentration. Well, if we have these little spacers right here, they're areas of significantly lower concentration, so we should see that they're going to expand or go underneath the gate polysilicon layers significantly less than if we had a very, very high concentration implant in that area. All right, now let's talk about oxide encroachment. Imperfections in the active area definition. This literally just, remember that the active area defines the holes that we cut out of the oxide layer to be able to do implantations and stuff like that. So if we have imperfection in the active area, we're going to observe oxide encroachment, literally just meaning that our width region isn't as large as we would expect it to be. Where the active area is reduced. Causing the width of the transistor to be smaller as effective width is equal to the drawn width minus twice the encroachment width. So effectively the exact same equation that we saw for lateral diffusion, but for an entirely different reason. And we can combat this by simply drawing our active region a little smaller, called bloat. So to compensate for oxide encroachment, the active region maybe exaggerated slightly. So we draw it slightly bigger than it needs to be to combat the effects of oxide, or excuse me, yeah, oxide encroachment. So, all right. So we have a transistor. I'm drawing a couple of different transistors here. It should be fairly obvious. So let's look at, I'm trying to find one. Let's go back to this guy at the top real quick, okay? So we have our P substrate here. So what happens when we have this N plus region from our source or drain implant butting up to our substrate? So there, the N plus region is in direct contact with our P-type substrate. What should we expect to see?
Some sort of PN junction.
Capacitance. Sorry, not.
All right. Well, so if I have N, oh, let's see who's in the chat here. Is your sound off? Maybe it is. Dang it. Thank you. Yes, because I was giving a test last night. Thank you, Alex. I'm sorry if I've been missing lots of stuff. I feel like an utter jackass. Somebody talk now so I can see if I can hear.
Can you hear us?
Yes. Great. I apologize profusely for doing that again. All right. So what's going to happen here?
It's going to see some sort of PN junction.
Yeah. So we're going to have a PN junction, and it's going to be hopefully reverse biased based on the signal. You know, we're going to be applying. Effectively, we're going to form another parasitic PN junction capacitor or a varactor diode, right? Just like we did when we had an N well. So we are now going to talk about source drain depletion capacitances, which is going to look pretty similar to what we saw for our N well to substrate depletion capacitances. All right. So the source and drain implants will form PN junctions with the substrate or NMOS or N well or PMOS regions, creating parasitic bottom and sidewall capacitances. So mathematically, we'll model this as Cj source or drain is equal to Cj naught B multiplied by ASD multiplied by our scaling factor squared divided by 1 plus VSDB divided by VBI B. I'm going to define what all these crazy symbols are in just a moment. To the MB power plus CJ naught SW times PSD times lambda divided by effectively the same denominator VSDB over VBI SW MSW. All right, where CJ naught B is the zero bias bottom depletion capacitance. CJ naught SW is the zero bias sidewall depletion capacitance. ASD is the area of the source or drain implant. PSD is the perimeter of the source or drain implant. Let's see. VSDB is the potential difference between the source or drain and the body connection. So before we move on and define a couple of things here, how many terminals does an NMOS transistor or a CMOS or a PMOS transistor have?
Should be
Three?
4, right?
Oh,
Yeah.
yeah.
Yeah, so it's 4. So the ones that you guys are probably most familiar with are simply gate, source, and drain, right? Those are the big ticket terminals, but there's also a body terminal, and that body terminal is what's used so you can get some control over the gate threshold or the threshold voltage of the transistor by playing about raising or lowering the body potential. So that's why here, this is, if we change the body potential, this is effectively this VSDB is effectively our applied reverse bias voltage, where we're allowing for the fact that we could potentially lower the body potential to make that larger, or slightly raise the body potential to make that smaller for a fixed value of an applied voltage at either the source or the drain. And we'll talk about body effects and how they influence the threshold voltage a bit when we get into our design portion of the class, which will be in about a week and a half's time. All right, so let's see, what else do we have? Then I think we just have our built-in voltages. Which is BBI comma V. For the body, PN junction, BBI comma sidewall. For the built-in voltage, for sidewall PN junction, and then M, let's see, B is the grading coefficient. For the body, PN junction, and MSW is then the grading coefficient for the sidewall. So lots of parts there, but here we can model the source and drain capacitances, parasitic capacitances fairly easily because it's, again, extraordinarily similar to what we saw with the N-well to substrate depletion capacitances. So same, same basic concept and all that kind of good stuff. Really the only changes that we're gonna see because the implants are so heavily doped as compared to the substrate, our unbiased junction capacitances aren't going to be proportional to the product of Na times Nd. They're only going to be proportional to, so if it's a p-type, it would be proportional to Nd, and if it's if it's p-type, it'll be proportional to, I'm trying to think what the opposite side would be. Yeah, so p-type would be proportional to Nd, and n-type would be proportional to Na, and that's just a function of the width of the depletion region. Alrighty, so we can also have source and drain parasitic resistances. And these are going to be maybe a little awkward to think about at first, but I think you get it. So let's say that we have the following layout drawing. I'll use this for my select. I define my active region in what may seem like a slightly awkward form, but we'll talk about it. Do my poly from my gate. Here's a metal 1 region to be able to send a voltage signal to my gate. I'll draw the via in just a moment. And then here's, for the sake of argument, my drain connection. And on the way over here, I might run into a situation effectively to where I have to extend my active region in order to route my metal properly. Let's draw our vias real quick. So, and I think I'm going to define a few widths so we can work an example problem based on this in a moment. So 1, 3, active. All right, I think I got everything written down here. So this length region, this kind of finger that's sticking out to the left, the extended active region adds a parasitic resistance in series with the MOSFET. Which can be determined by specifying the number of squares in the source drain region as N R S D is equal to the length of the source drain region divided by the width of the source drain region. And then our resistance is simply the number of squares multiplied by the sheet resistance of the source drain region. So if we're looking at this particular example, that line is not remotely straight. And we're asked to estimate the parasitic resistance of the source and drain regions of the NMOS transistor if R square S is equal to R squared D is equal to 100 ohms per square. And it looks like I'm missing one piece of information. Yep, pretty obvious one. So we're obviously going to need this dimension, which is 3 grid units. And we're going to need this dimension as well, which is 10 grid units. Alrighty. So from this, the number of squares in the source region, right? So it's going to be the length, which is this 11, divided by the width, which is this 3, gives us a source series resistance of 367 ohms, so fairly appreciable. And on the drain side, our length is 4 and our width is 10. That gives us a drain resistance of 40 ohms. So from a schematic standpoint, and I'm going to make the assumption here that the source and body connections are tied together. I don't have any particular reason to assume that. I just am. This is what our transistor model would need to include. So when we play around with electric literally in just a few minutes at this point, we are going to have options, and it's going to tell us the design rules for like while we're playing around with stuff about how things need to be spaced and how we can minimize these parasitic resistances actually pretty easily. And so I'll illustrate that in just a couple of moments. All right, so the last thing that I want to talk about then is laying out long transistors and wide transistors. And then we'll get into actually using our layout tool. All right. So we'll first look at this from a schematic style view, right? So let's say that we have a transistor, single transistor. Oops. Right. And we wanted to orchestrate a way. So let's say the ratio of this guy is 5/20. So that's the width over the length there. We could, instead of drawing one that has a really, really long, or a really, really long chunk of polysilicon, we could break things up into effectively little fingers. And so what I mean by that is we could have three transistors in series. All their gates are tied together. So this is gate, this is our drain, this is our source. So this would be our drain, and this would be our source. But this particular transistor could be 5 over, let's call it 10. This guy could be 5/5. And this guy could be 5/5. So we could string 3 resistors in series and attach all their gates together to get an equivalent long length transistor. So what that might look like from a layout perspective, in a general sense, let's say we have our active region like so. Way over here on the left-hand side, we'll have our metal 1 connections, which is forming our ability to send a signal to the drain. And a similar thing way over on the right-hand side. So this is our source. And then as far as our gate goes, we might have fingers like so. All right, so one that's a little short, one that's a little short, and one that's very wide. Like so. So this would be R5, R5, and R10, and we get the overall effect. So we're able to draw it this way. Notice that, so here's the drain of our leftmost transistor. This guy right here is the source of that same transistor, and the drain of the one to its right. Same thing here. This is the source of that middle transistor, and then the drain to the one that was right, and so forth. So we're able to combine these transistors in series like so, by using just one large gate. We don't need to pass any signals on or off from these points of interconnection here. So this is one way to do a long length transistor. We're not going to see a whole lot of long length transistors in our designs or anything like that. We are, however, going to see probably a bit. If we use a design similar to last year, I think there's literally one long length transistor, and I modeled it both using interdigitated fingers like this and as just a large chunk of polysilicon, and it didn't seem to make very much of an appreciable difference on the performance of the device. Now, to set up long width transistors, which we will have a bit of those, and one of the biggest reasons is that the mobility of holes is not the same as the mobility of electrons. And so in a in a current mirror, which might be using, say, a PMOS active load, in order to get the same current flowing through both the PMOS sections and the NMOS sections, the PMOS ones will have to be larger so that the overall W over L ratio, or the mu times W over L ratios are the same, so that we're getting the same amount of current through effectively both sets of transistors there. So to make long width transistors, we effectively just wire transistors in parallel. So if we had something like this, where we had 4 transistors, we tied all of their gates together, we tied all of their drains together, and we tied all of their sources together. So gate, drain, and source. This is electrically equivalent to a single transistor that has a 4W over L. So if all of these guys have a particular width to length ratio, when we tie them all in parallel, we get 4 times the width. So let's look at that real quick from a layout perspective. That should be good. Might be too much active, but that'll be okay. So we've got our big chunk of active. And what we would do is, so let's see, that's the wrong color. Here's our poly. And so we'd have interdigitated polysilicon fingers again, like we saw in our other design. Too long, but that's okay. So here's all of our gates tied together. Now we need our sources tied together, which would be done on a metal 1 layer. So now all of our sources are tied together, and I'll draw the B as in later. And then lastly, tie our drains together. So we can split this guy. So over here on the left-hand side, we have source, gate, drain. So that's one transistor. Then for the next, we have drain, gate, source. So that's two transistors. Source, gate, drain is our third transistor. Drain, gate, source is our fourth transistor. So we've actually been able to probably minimize the footprint of this guy by having this interdigitated structure. And using this technique like this, where we have the interdigitated thing, actually goes along really, really well with what's called a common centroid layout, which we'll talk about later, where common centroid layouts are used to minimize the effects of process variations in our design. So if you want two identical resistors, you want them to be equidistant from a central point so that they have the exact same, effectively the mismatch balances each other out. All right, so let's take 5 minutes or so as a break, and then when we come back, we will play around with electric a little bit. Since I had things on mute, for the few of you who are unable to get electric to work, have you tried to resolve anything, or have you just been listening to me rant about stuff? That sounded like robot noises to me. Okay.
Dr. Hartman, I couldn't open the electric jar file. So I downloaded the 32-bit and also 64-bit Java. But whenever I downloaded the electric jar file, it's I mean, I'm double clicking, but and a black window pops up and then it's gone.
What operating system are you using?
That's Windows 64-bit.
Windows 10, 64-bit? Windows?
Yeah, Windows 10, yeah.
Okay. Let me look at stuff real quick. All right, I found a couple of links about running a command prompt, which a couple of students last year, or at least one student last year had to do. I'll send you those links after class so that we don't bog down everybody trying to troubleshoot with file path, all that kind of good stuff. Okay, so let's see. And this is being recorded, so everybody should be able to see things. So if and when you're able to open electric, this is roughly what it should look like. Just trying to make things work for me a little bit here. And so today we're really just going to play around and talk about some of the features in a few of the homework assignments that I uploaded. Excuse me. It specifically asks you to do a layout on some. So I kind of just want to do a very brief overview of what can be found here, and then let you guys have the rest of the class period or whatever to just, try to make some very simple circuits. So like maybe a common source amplifier. So just a transistor in series with a resistor kind of thing. All right. So anytime we're going to make any type of layout, we need to go into the Explorer tab and create a new cell. And we can create either a schematic, which we'll be doing some hopefully on Thursday, icon, layout skeleton, on all kinds of stuff. Lots of different things that we can do. Today we're just going to be messing specifically around with layouts, and we can choose actually the technology that we are developing a layout for. For us, it's going to be MOCMOS, M-O-C-M-O-S. And we need to give it a name. So it's very vocal about when we screw things up. Got my keyboard attached to my laptop. So I'm just going to call this guy simple. The names for your cells can't include spaces or anything like that, so you're going to have to use underscores, etc. It won't give you an error for that. It just won't create the cell. All right. So now we go back to components because we're in our cell. And so over on the left-hand side here, I don't know if you guys can see down in the bottom left-hand corner, whenever I'm mousing over this yellow thing, it says at the very bottom left-hand corner, use arc metal 3. So this is how we draw on the metal 3 layer. Arcs are what electric considers to be wires. So if I click on this and then I click out here, it's really not going to do anything because I don't have anywhere to connect things. So notice in the messages, it says must start new arc from one node or arc, or wire two nodes or arcs together. So I can't just start with a wire out in free space. It doesn't care for that. Purple is metal 2. This blue is metal 1. Here we have polysilicon 2, poly 1, an N active region, and there's a little arrow here. So we can switch it between N active and N wells. Here's P active and then P wells. And then way down here at the very bottom left-hand corner is built-in models for transistors, which there's other ways to do that in a moment. But then we can do poly 1, poly 2 capacitors, poly 2 high resistance, poly 2 resistors, P active resistors, N active resistors, P well resistor, N well resistor, poly resistors, et cetera, et cetera, et cetera. So this is how we're going to be making capacitors and resistors particularly in this class, so we won't need to build them from scratch. We'll simply be editing pre-built versions. All right. Here we have nodes and all that kind of stuff for the metal 3, metal 2, metal 1, poly 2, poly layers, etc. And then this is an N active pin node, and we can change that to N well. Same here, and then we are able to just put in P wells. And then down here at the bottom, on the middle column, we can choose from the different variations of transistors, where if we want it the basic transistor, thick, or scalable, we're just going to leave things alone here. And then finally in the third column, this is our how we kind of switch between layers. And so what I mean by that is we don't have direct access to the layers where we put in our contacts or vias. So instead, this guy right here creates a metal 2 to metal 3 contact. Then we have metal 2 to metal 1 contact. Then we can do metal 1 to poly 2 or metal 1 to poly 1. This guy is, let's see, metal 1 to poly 1 by default. Okay, so the one above it is metal 1 to poly 2, and then metal 1 to poly 2 to poly 1. So it's like a 3-layer contact. Then we have this guy, N active, which we'll be using quite a bit. I'll talk about that in just a moment. P active, then we have our N well, and NMOS. All right, so let's create a simple NMOS transistor here. So hopefully everybody can see what's on my screen. This outer region of brown slashy lines, that is just saying that that's effectively my P well, I believe. So it's my substrate in other terms. Then we have the region of the transistor defined. And the green region is either going to be my source or drain. The pink thing that's overlapping the green regions is my polysilicon. So for right now, I'm going to rotate it. So if I go to edit and then rotate, I can choose. It wouldn't particularly matter whether I go clockwise or counterclockwise, but for some reason, only counterclockwise has a keyboard shortcut. So so there are different parts of this thing. So can anybody see like the little blue plus sign on the top of the pink poly region?
Yes.
I can't. I think the screen might be frozen. I can't see it.
It's really tiny.
Yeah.
Oh, I see it. I barely see it. Yeah, the resolution is just weird.
Yeah, it's super duper small. So that's defining one of the nodes on this guy, right? So if I click on that and then I right click out in space, I've just created effectively a wire out of polysilicon. So that's how I'm gonna run lengths of things. Now, I might wanna connect. So if I click over here, if I clicked over the green region, you can maybe just barely see a little bitty plus sign excuse me, on the right-hand side. This would allow me to extend my active regions on the source or the drain and stuff like that. And there's going to be times when you're going to have things stacked on top of each other. And so you're going to have to shift left clicked to select other things. So for instance, if I click on this, it's showing me that plus sign on the poly, which means I have the poly region selected. If I shift click, now it's selecting that middle region of overlap, and it's gonna kind of alternate between those two things. The more things you have stacked up, the more options that you're gonna have. All right, so if I double click on my transistor. Now I get to be able to edit some parameters here. So let's say for the sake of argument that I want to make a 10 by 2 transistor. I can just change my width to 10, leave my length alone. I can change the rotation. I can change the position of it. I can mirror it left and right, up and down, all that kind of stuff. Here are the different ports that's telling me how I can connect things to it, etc. So I'm just going to change it to a 10 by 2 and click OK. So a little bit more room to play around with here.
Dr. Harmon?
Now, yes.
FYI, unless it was just me, I don't think we could see the pop-up windows.
Son of a bitch. Okay. I don't know how to.
Yeah, I think that's a Zoom thing.
Huh. Well, that's going to complicate things quite a bit.
Dr. Harmon, I'm still stuck on how you make it like expand or whatever. Like if you drag a node, make it longer.
Okay, so let's revisit that real quick. So I've clicked on the poly so that I have access to the poly, and then I right click out in space, and that's what drags it out. If I click here, now instead of seeing a plus sign because the region is a little bit larger, I have this box. And so if I right click out in space, I'm going to extend that active region. If I click over here, I have access to this one. I right click, I extend that active region, and I can extend my poly down like so. So it's all about clicking, it's effectively clicking on the material that you want to extend and then right clicking where you want it to go.
Got it. Okay, thank you.
All right. So, So right now, this transistor has a gate and then a source and a drain, but we don't have any, say, metal connections or anything like that to it. So we're going to need to include those. So because this is a NMOS transistor, I'm going to need to put N active regions, one on each side. If I double click, it's going to pull open a pop-up window that you guys can't see, which frustrates me to no end. So I'm going to change the X size of this, no, the Y size of this to 10 to match my transistor size. And I'm going to do that on both sides. Oops, I did the wrong one. So double click, move it back to 5, change that to 10. Okay. 5, 10, 5, okay. So the reason why I have to do this is because the transistors in electric don't come with metallic contacts to be able to connect things. So I have to, so this N active thing right here that I have on the left-hand side and the right-hand side of my transistor is a metal 2 layer with 2 vias stacked on top of an N plus implant. So to be able to connect a metal layer to, or to connect metal to my transistor, I can right click on that N active, or excuse me, left click on that N active and then right click on this region. And now these two things are electrically connected by effectively a N plus resistance, very similar to what we had in that last example problem that we worked, okay? So we put a series resistance between our metal contact and the source or drain of this transistor. Now we can make that resistance smaller by simply left clicking on our active and dragging it in. Can everybody see the little message above where it says N active spacing is 14.5.
Yep.
Yes.
Okay, so if I move it closer and closer and closer, it's telling me what that spacing is. If I get to 3, that should be the minimum. And if I go any further, it tells me error. N active spacing is 2.5, minimum is 3. So it's constantly running some small form of design rule checks in the background at all times to just let me know, hey, I'm doing something right or I'm doing something wrong. Another way that we can look at whether or not we're having design rule issues is to go to Tools and check hierarchically. So right now it says there are 0 errors and 0 warnings found. So that's good. Now I could left click this guy, right click over the active region. Now I've connected this, and let me move it down so that I don't have weird things here. Like so. I can send the signals to the source or the drain. Let's say that I wanted to create a metal contact to the polysilicon layer. I would use this guy over here, metal 1 polysilicon 1-con, means it's a contact. I'm just going to drop it there. Let's see if it gives me an error by putting it there. I think it might until I connect them together. Oops. 2 errors, yeah, so I hit the wrong thing, but. Yeah, so it found 2 errors and 0 warnings. So we go to Explorer. Now that we have errors, it saves all of them that we run. So we're seeing spacing layer polysilicon 1 to node metal polysilicon 1 blah 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 is less by 1.5 than 3 to the transistor. So rule 3.2. So I'm currently violating rule 3.2. It lets me know that, and it highlights in red flashiness the issues there. And it's telling me that the transistor is too close. So the first error tells me that the contact is too close to the transistor. The second error tells me that the transistor is too close to the contact. So I can resolve this by left clicking and then right clicking the poly. And now they're connected. If I run my DRC, no errors. So it's going to let you know when you mess things up. I would argue that you should be running the DRC probably, goodness gracious, at least every couple of minutes, if not every couple of steps that you're doing, just to play around with things and make sure things are okay. Excuse me. So we can move this closer, and it's telling us now that the metal spacing, it gives us an error. So we can, it tells us when we bring our contact in too close to the metal of our source and our drain, because these will arguably have different potentials, and it's using that design rule to tell us what the threshold is. Now let's put in, so we have, let's see. So right now I've clicked on this left active region, and I believe it is giving me my active. If I shift click, I'm trying to get to my metal. Yeah, it's just doing that. So another way to do this to be, if I click on the metal 1 layer, oops, I zoomed out. How do I zoom back in? All right.
You can control scroll.
Yeah, so your wheel goes up and down, shift goes left and right, and yeah, control is zoom in or out. Thank you. So I'm trying to select this pesky metal layer here because I want to maybe run a wire up or something, and it's being arguably difficult. There we go. So now I have a metal wire that's telling me that my spacing is far too close. Now I accidentally moved this thing. That's not remotely what I wanted to do. So we just got to get used to this. It's going to be kind of finicky. There's a big fat metal wire to the left that's useful. A big fat metal wire to the right, so we can play around with that kind of stuff. Another thing that we're going to have to use, or that not necessarily that we should be using, is these N-well and P-well connections down here towards the bottom, right above PMOS and NMOS. These are our body connections. So for this NMOS transistor, we want to connect to the P-well because the P-well is our substrate, okay? And we need to be able to connect to the P-well so that we can ground the substrate close to the NMOS transistor so that we know effectively what the source body voltage is, the drain body voltage, et cetera, so that we're not introducing any body effects. So there are rules as to how close this guy can be. So it's the P active to N active. And it tells us that the minimum is 3. So this is as close as we can make it. Let's see. I think because those kind of gold areas overlap, it might give us an error. Yep, found an error. But if I back them up to where they no longer overlap, no more errors. So this is a, excuse me, completed NMOS transistor. And we could do effectively the exact same thing for a PMOS transistor, except that we would need to make a connection to the N-well to ground its local substrate. So there's only 10 minutes of class left, but I think the first homework assignment thing that I posted on Moodle for you guys to potentially play around with is making a simple inverter circuit. I believe that most of the undergraduate students had to do that in 336. Is that right?
Yes, yeah, we've
Play on.
dealt with it.
Yeah. So, you know, right now I'm not really concerned with what you make, just as long as you're familiarizing yourself with electric a little bit. And again, run the design rule checker often to make sure that you're not introducing errors and all that kind of stuff. So pull out an old textbook or something like that on analog electronics and just try to make some very, very simple amplifier building blocks. So, you know, common source, common drain, all that kind of good stuff, just to play around with electric and familiarize yourself with how it works. So if we have this transistor, let's say that we wanted to throw a high-res poly 2 resistor in the mix, and we wanted to put it in series with our, I'm going to call this guy the drain just because. I'm going to, nope, scroll out a little bit. So this is our resistor. So the red area, so the area with that red square, that is effectively the layer that shields that polysilicon from getting doped. So it defines the actual resistor part of your high res resistor. So we could connect over to our metal region, and now they're wired together. If we double click on this, and I know you guys can't see anything, it's telling me that the length is 40 and the width is 10. Even though this thing is obviously significantly longer than that, what we are controlling is the resistive area. So right now, this is 40 by 10, so it's 4 squares, with each square having a nominal resistance of about 1 kilo ohm per square, I believe, according to the notes. So this is a 4K resistor. If we wanted to make a 10K resistor, it would have to be 100 in length and 10 in width, which would be maybe appreciably long. So instead we could run a serpentine pattern, right? So let's make this a 50. I'm making another one, I think, yeah, right down here. How close can I get these? So this is the smallest I can make it. Now, connecting these two guys together like so, it's a 5K in series with a 5K gives me a 10K. So you can play around with things like that, you know, to make the larger resistors with minimizing footprints and things like that. Alrighty, that's enough out of me for today because I'm having trouble breathing. I'll try to post some stuff online for those of you who aren't able to get electric to work regarding how we can use the command prompt to get it to work. If that doesn't help you, then I should be in my office tomorrow. Let's see, from our, what time do I get out of class? I can be in my office tomorrow, I think from around 8 to 10. And then also from maybe 2:30 to 4 if people need help. But please send me an email or shoot me a text to let me know that you're coming, because I have a tendency to roam around and all that kind of stuff trying to get things done. Alrighty, so again, that's enough out of me. Hopefully you guys will have some fun playing around with the layout tool, and I'll see you on Thursday.